welcome to this week's weekly review session. I believe we're at week 6, I believe. So right now, today we're going to be covering the product rule and the quotient rule, as well as trig derivatives, and we're going to touch on some trig limits as well. So first, let's go ahead and move into our product and quotient rules. So first thing we're going to cover today is the product rule. So our product rule states that if we have two functions, f of x and g of x, if they are both differentiable, then the derivative of the product of f of x and g of x is going to equal our initial function f times the derivative of our g function plus our g function times the derivative of f. So now that we have this stated, let's go ahead and try to work a little bit with this. And if we also want to put this just purely in prime format, we could also rewrite this as f times g prime equals fg prime plus gf prime, just to make that a little bit cleaner to read. So now let's go ahead and try to work a couple of examples. So now let's say we have a function. So let's say we're wanting to find the derivative of 3x plus 2 times e to the x. Alright, so one way we can go ahead and solve this is we can go ahead and break this up into two functions. We can say that we have 3x plus 2 can be f of x, and then we can let e to the x be its own function, g of x. So now let's go ahead and work and see and set this up. So we know that our f of x is going to be equal to 3x plus 2. Therefore, and then now we have to go ahead and find our f prime of x. So we go ahead and use our power rule. So we get 1 times 3, which is 3, times x to 1 minus 0, which is just 1, so we just get 3, and then the derivative of that 2 is just going to be 2. So therefore f prime of x is equal to 3. Now we have our g of x is equal to e to the x. Well, as we learned last week, the derivative of e to the x is just going to be e to the x. So now that we have our two functions and both of their derivatives, we can set up our rule. So once again, as our rule states, if we have two functions multiplied together, their derivative is just going to be the first one times the derivative of the second plus the second times the derivative of the first. So we can just go ahead and now plug everything in. So now we just have d over dx of our initial function, 3x plus 2 e to the x, equals our f of x is going to be 3x plus 2, our g prime is e to the x, plus our gx is e to the x times our f prime, which is 3. So now we can clean this up a little bit and say that we have 3x plus 2 e to the x plus 3 e to the x. And if we really wanted to, we could even go one step further and plug this 3 in here and say that we have 3x plus 5 e to the x as our final answer. Now, that one was a fairly simple problem, but now let's go ahead and try another one that may be a little more challenging. So for this one, what they're wanting us to find, what we're going to find is the derivative of, we have the cube root of x squared plus 2x squared times the fifth root of x plus 1 over x. All right, so we have this set up. So now let's go ahead and see if we can clean this up a little bit and just rewrite it just so we can kind of get a better idea, so we can go ahead and just get it cleaner in case we need to ever use power rule in this. So now let's think of this. This cube root of x squared is actually going to be equal to x to the 2/3. And then our 2x squared can stay the same. Our x to the fifth root can be written as x to the 1/5. And then we have our 1 over x can be written as x to the negative 1. So now we have to go ahead and start finding the derivative of this. So now let's go ahead and try using our product rule one more time. So let's go ahead and just break this up by the parentheses and say that we have our f of x and our g of x. All right, so now let's go ahead and figure it out. So now we have our f of x equal to x to the 2/3 plus 2x squared. Therefore, f prime of x, we're going to use power rule on both of these, so we can pull that 2/3 down, and our exponent becomes negative 1/3, plus, we can pull this 2 down to get 4 times x to the 2 minus 1, which is just 1, so we can just leave it as 4x. Then we now have our g of x as well. So our g of x is equal to x to the 1/5 plus x to the negative 1. So once again, we're just going to use power rule right here. So we can pull down this 1/5 and get x to the negative 4/5 minus, when we pull that negative 1 down, we get x to the negative 2. All right. Now that we have that, we can go ahead and start setting up our actual product rule and our quotient rule. So we now have, let's go and erase this. So once again, we're trying to get this set up to where we have our f times g prime equals f times g prime plus g times f prime. So now let's go ahead and set that up. So we already established that our f of x is going to be x to the 2/3 plus 2x squared. And then we're going to multiply this times our g prime, which is going to be 1/5 x to the negative 4/5 minus x to the negative 2. And then we're going to add all of this to our g of x is going to be x to the 1/5 plus x to the negative 1 times our original f, which is, times our f prime, which is going to be 2/3 x to the negative 1/3 plus 4x. All right, so now let's go ahead and start to go ahead and distribute everything. So we're going to go ahead and we're going to get x to the 2/3, and we're going to distribute that out to both parts of this function. So we get x to the 2/3 times 5th x to the negative 4/5. So we're going to go ahead and say we for sure have a 1/5 x. Now the exponent, so we have a 2/3 and a 4/5. So what we can go ahead and do is we can actually go ahead and combine those using our property saying that if we are multiplying the same base to two different powers, then we can just add those powers together. So what we can do is we can, or subtract. So what we can do is we can say that we have x to the 2/3 times x to the negative 4/5 is just equal to x to the 2/3 minus 4/5. So now let's just go ahead and get that 2/3 minus 4/5 and figure out exactly what that is. So what we can do is we can say we have 2/3 and 4/5. So let's go and just find a common denominator. So we're going to get 15. All right, so we have 2 times 5 is 10 minus 3 times 4 is 12 over 15. So we get negative 2/5 right up here. And then now we have x to the 2/3 times negative x to the negative 2. So we're going to get a minus x. 2/3 minus 2 is going to be negative 4/3. So now we have that one done. Now we have to look at the other side. So now we're going to go ahead and get 2x squared times both of these terms again. 2x squared times 1/5 x to the negative 4/5 is going to get us 2/5 x. So now we have 2 minus 4/5, which is actually going to go ahead and just give us 6/5. And then we have 2x squared minus x to the negative times negative x to the negative 2. Well, that 2 and negative 2 and the exponents are just going to cancel out, which is just going to leave us with a minus 2. Now let's move on to the next step. Over here we have x to the 1/5 times 2/3 x to the negative 1/3, and then also with 4x. So x to the 1/5 and then x to the negative 1/3. We know 2/3 is going to be our coefficient. We get x, so we get 1/5 minus 1/3. So over here we're going to get 1/5 minus 1/3, and that is going to be, once again, a common denominator of 15. When we cross multiply, we get 3 and 5, which is just going to leave us with negative 2/15. Actually, let me fix this one right over here, because that one, there we go. There we go. That one got a little messed up. There we go, though. We have that fixed now. All right, so actually, let me make it worse. There we go. Negative 2/15. There we go. All right, that's fixed now. So now let's move on to this 1/5 x to the 1/5 times 4x. So that's just going to get us coefficient of 4. X, and that's just going to be 1 plus 1/5, so once again 6/5. Now let's move on to that last set of terms where we can get x to the negative 1 times both of these terms. So x to the negative 1, we're going to get plus a 2/3 negative 1/3 minus 1 is going to be negative 4/3. And then we are going to get, we're going to keep that 4. And then it's going to be x, so we get x to the negative 1 times x to the 1. That 1 and negative 1 exponents are going to cancel, so we are just going to be left with x to the 0, which is just 1. So now let's go ahead and see if we can go ahead and combine any of these terms. So we can see that we have a couple terms with negative 2/15 in the exponent. So that's going to get us, so we have 1/5 plus 2/3. So over here, what's that? 1/5, 2/3. We're going to go down to 15 for our denominator, and that's going to get us 3 plus 10, and that is going to get us 13/15. X to the negative 2/15. And then we see we have a couple that have negative 4/3. So that one we get a negative 1 x to the negative 4/3 plus 2/3 x to the negative 4/3. So that's going to just leave us with a negative 1/3 x to the negative 4/3. We have a couple that have 6/5. So this one we get 4, and then we get 2/5. So we just have to add those together. So let's just go ahead and just combine that. Let's just have fun and combine decimals and fractions. That way we can just even this out. So we get 4.4 x to the 6/5. Lastly, what we can do is we have this negative 2 and this 4, which is just going to leave us with plus 2. Therefore, this is going to be our derivative to the previous problem. Yeah, so this is just going to be equal to d over dx of the cube root of x squared plus 2x squared times the 5th root of x plus 1 over x. But let's actually go ahead and try something else. Since this one was kind of a lot of work, let's go ahead and try something else and try another method to solve this. So let's go ahead and try this once again. So now we're going to go ahead and stay at that point. Now let's go back to the point where we just cleaned up the function. Just back to where we had x to the 2/3 plus 2x squared times x to the 1/5 plus x to the negative 1. Now let's try this again. And this time we don't want to use product rule, because product rule, we've seen how that one works. So let's try this one more time. And let's actually go ahead and let's go and try to distribute and see if we can actually use our power rule. So first let's go ahead and distribute this x to the 2/3 with the entirety of the second term. So we get x to the 2/3 plus 1/5. Well, 2/3 plus 1/5, as we saw earlier, is actually going to get us 13/15. All right, and now we're going to go ahead. And then for that second term, we get x to the 2/3 minus 1. So we get x to the negative 1/3. We're going to distribute, and now we can go ahead and distribute this 2x with both terms. And this time we're going to go ahead and get 2x, and we get 2 plus 1/5. So that is going to be Yep, 2 plus 1/5, which is going to be 11/5. And then 2x squared plus times x to the negative 1, which is going to get us 2 times x to the 2 minus 1, which is just 2x. Now let's try deriving this, and because now we're actually in a form to where we can actually just go ahead and use product rule the whole way. So if we look at these first two terms, we can get x to the 13/15. Well, we can pull that 13 over 15 down. And then 13 over 15 minus 1 is negative 2 over 15. Now for the next term, we can pull that negative 1/3 down. And that's going to get us x. And then we get negative 1/3 minus 1, which is 4/3. Now we're going to get 11 over 5 times 11 over 5 times 2. So we're going to get 22 over 5 x. And we get 11/5 minus 1, which is going to be 6/5. And the derivative of 2x is just 2. Yep, this looks pretty much what we had earlier. Let's just double check this 22 over 5, which is going to get us 22 over 5 is going to get us 4 and 2/5, which is 4.4, which is what we had earlier. So this is this essentially gets us. This is the same thing as we actually had earlier. This just shows that you can actually manipulate your functions to kind of go ahead and see if you can get in you want to use, to go see if you can find another way to derive it. Because sometimes there are different methods to go ahead and do it. Yes, our initial setup was for product rule, but we were able to manipulate it and get it into something that was much easier to work with. So sometimes your prof may say you have to go ahead and solve it in this way, but sometimes they leave it up to you to go ahead and figure out what is easier. All right, so now let's go ahead and move on to our quotient rule. So our quotient rule it states that if we have two functions, f of x and g of x, so f and g are differential, then the derivative of f of x over g of x is going to equal g of x minus the derivative of f of x. Wait, that's a times. Excuse me, I misread my notes. G of x times the derivative of f of x minus f of x times the derivative of g of x. All over g of x squared. Or if we want to put this in prime notation, what we can say is that f of x over g of x, that you can go ahead and say f over g prime equals to g times f prime minus f minus g prime, all over g squared. Or sometimes if you want to get this out of terms in f of g, we can also, another good way is actually what my high school Cal teacher taught, and he put it in terms of saying that this equaled our low, which is our denominator, d that's the derivative, high, minus high d low over low low, if you want to put that in terms of words. And just get that less technical. But essentially, it means the same thing. You have your low, which is your denominator, times the derivative of your high, minus the high, which is your numerator, times the derivative of your low, over essentially what is your denominator squared. So now let's go ahead and move forward and try a couple of examples. All right. So now let's go ahead and try an example saying we have x squared plus 2x plus 3e to the x all over x minus 4. All right, so we can say that we have that the numerator is our f and our denominator is our g. All right, so let's go ahead and set this up. So we know that our f of x is equal to x squared plus 2x plus 3e to the x. And then our f prime of x, once again, we can use power rule for the first term, which is just 2x. The second term, once again, power rule, plus 2. And the last one is our exponent rule, which just leaves us with 3e to the x. And now we have our denominator, which is our g, which is our g of x equals x minus 4. So now we have our g prime of x. The derivative of x is just going to be 1, and then that negative 4, when you derive that, it's just going to be 0, so our g prime is just 1. Now let's go ahead and start plugging this in. So we're going to get we have our denominator function, which is x minus, so once again, let's just rewrite our problem. Actually, first let's rewrite our problem. So where we have all right. So now let's go and get this up. So we know that our bottom function is x minus 4, so we can go ahead and say we have x minus 4 times our derivative of our numerator, which we said is going to be 2x plus 2 plus 3e to the x, minus our numerator, which is x squared plus 2x plus 3e to the x, times the derivative of our denominator, which is just 1, all over the denominator squared. All right, so now let's just go ahead and see if we can clean this up, see if there's any terms we can combine, and then we'll be done. So the numerator, we get, let's distribute both of these terms out. So we have x times the whole second term, which is going to get us 2x squared plus 2x plus 3x e to the x. You can distribute out that negative 4 to all of these terms. So we get minus 8x, a minus 8, and a minus 12 e to the x. And then the second term is just a lot easier. We just have to distribute out that negative and done. So we have negative x squared minus 2x minus 3e to the x in our numerator. So now let's go ahead and we can combine any terms. So we have a couple of x squareds. So we get x squared. Let's see, we have a few x's, so we get 2x, negative 8x, negative 2x. So we are left with a negative 8x. All right, we have a couple e to the x's, so we have these two e to the x's. We get negative 12, negative 3, so we get minus 15 e to the x. And let's see, only two terms we have left unaccounted for do not have any partners, anything to cancel out with, so we're just left with that. Plus 3x e to the x minus, all right, and then minus 8. This is going to be all over x minus 4 squared, and unless they ask you specifically to roll that out and make that and expand that denominator, I would just leave it as that. So now let's go ahead and try something a little different. Let's say that we have a function h of x. And h of x is equal to g of x times f of x. And let's say that we know that f of x is equal to 2x squared plus 1, and we know that g of 2 is equal to 4, and g prime of 2 equals 1. What we want to do is we want to find what is h prime of 2. All right, so we know that h prime is equal to g of x times f of x. Then we're going to go and go back to product rule, and we're going to try this again with quotient rule in just a second. So we have this problem, g of x and f of x. So we know everything in terms of g, but we don't know exactly in terms of f. So what I would do first, let's go ahead and get our f of x is 2x plus 1. And what I would do is I'd find our f prime of x. We get times 2 is 4 times x to the 2 minus 1, which is just 1, and derivative of 1 is just 0. From here, what I would do is I'd go ahead and find these values in terms of 2. So we get f of 2, which is going to be 2 times 2 squared plus 1, which is going to equal 8 plus 1, which is equal to 9. F prime of, so now we want f prime of 2, which is just going to be 4 times 2, which is 8. So now from here, what we can actually do, even though we didn't have a function for g, what we can do is we can plug in all of our values, knowing that if we have h prime of, if we know that h prime is equal to g times f prime, we can just plug in into our initial product rule, knowing that we have g times f prime plus f times g prime. We can just plug everything in, so we know that our g of 2 is equal to 4. And we know that our f prime is 8. Our initial f was 9, and our g prime is 1. So that can just get us 32 plus 9, with 41 being our final answer. But now let's try this again, but let's say this time h of x is equal to g of x over f of x. In the end, we still want h prime of 2. Well, it's essentially a very similar concept. We don't necessarily have a function for g, but we have values for g at the point that we want. And we also have an x, and we can find our values for f at a specific point. So we can actually still just plug this straight into our quotient rule. Since we know that h prime is equal to g over f in this case, prime, we can say that we have f times g prime minus g times f prime all over f squared. So we can go ahead and just plug everything in and say that we have our f of 2 is equal to 9. Our g prime of 2 is equal to 1 minus, we have our g of 2 is equal to 4, and then our f prime is equal to, and our f prime of 2 is equal to 8, all over our f of 2, which is 9 squared. So this would just get us 9 minus 32 all over 81. If you want to go a little further and do 32 minus 9, that would go ahead and get us 23. So we'd be left with negative 23 over 81. So if you ever are stuck in a situation where you may have a table of values, but you don't necessarily know a function, you can still go ahead and apply it on your derivative rules. You just have to be able to know when and where to plug things in. All right, so now let's go ahead and move on to trig. Now, first thing I want to do is actually cover our trig derivative rules. So, when we're looking at trig, there are two main rules that we need to know. And once we know these, we can actually go ahead and apply this to a lot of things involved in trig. So, the first rule that we need to know is that the derivative of sine of x is equal to cosine of x. And then we also need to know that our derivative of cosine of x is equal to negative sine of x. All right, so now that these two rules, we can actually use these to find pretty much any standard trig rule and they can just be used in general derivatives, or just in combination with our other rules. So first, let's do just a couple really quick examples involving we're going to use just a couple really quick examples involving pretty much just sine and cosine. So the first example I want to do is find the derivative of 3x plus sine x. So if we do this, we can go ahead and just apply our rules. So if we derive 3x, that's just going to be 3, correct? And then if we derive sine, that's just going to get us cosine of x. Yeah, because the sine and cosine rules really can be just that simple. So now let's try another one involving cosine. This one we want to find the cosine of x over x squared. So now let's actually go ahead and try to get a little bit of practice with our quotient rule. So we can go ahead, we know our cosine of x is going to be our f, and our x squared is our g. So we're going to go ahead and say that we have our g, which is our x squared, times the derivative of our f. Well, the derivative of our f is just the derivative of f equals cosine of x is equal to negative sine of x minus, we know that our initial f is going to be cosine of x, and the derivative of our x squared is just 2x, all over our x squared to the fourth. We just have to clean this up a little bit just to make it a little prettier to read. And essentially can say is that we have negative x squared sine of x minus 2x cosine of x over x to the fourth. And we can even go one step further, since we have x's in our denominators and we have x's in both of our terms. We can actually go one step further and just eliminate that x to where we are left with negative x cubed. Negative x sine of x minus 2 cosine of x all over x cubed. So now let's try something a little different using our rules. So most of our trig functions are actually based solely off of sine and cosine. So knowing that, let's go ahead and try to find the derivative of tangent of x. Well, tangent of x is equal to sine over cosine. So really what we can say is we're finding the derivative of sine of x over cosine of x. From here, it's essentially just applying our quotient rule again. So what we can do is we can say that we have our bottom is cosine of x times the derivative of our top, so the derivative of sine, once again, is just cosine, minus our top, which is sine, times the derivative of our denominator, so the derivative of cosine is negative sine, all over cosine squared of x. So now if we combine this a little further, we can say that we have cosine squared of x minus sine of x times negative sine of x. So we can actually go ahead and cancel these negatives. So we get plus a sine squared of x all over cosine squared of x. We can, using our Pythagorean identity, we can actually cancel out the top to just 1, which gives us 1 over cosine squared of x, which is equal, since 1 over cosine is secant, we can say this is just secant squared of x. Therefore, the derivative of tangent of x is equal to secant squared of x. All right, so now let's move on and try finding the derivative of cosecant of x. Well, what we can do is we can actually go ahead and say, similar to how we did the tangent problem, since we know cosecant of x is equal to 1 over sine of x, we can just say we're deriving 1 over sine of x. Well, we can go ahead and actually, even though that's just a 1 in the denominator, we can actually still treat that as a function. And we can go ahead and still apply our quotient rule. So that's going to be our f, and we're going to have our g right here. So let's go ahead and move forward with our quotient rule. We know that our bottom is going to be sine of x. The derivative of 1 is just going to be 0, minus our numerator is just 1, and our denominator is going to be, and our denominator is sine of x, and the derivative of that is just cosine of x. This is going to be all over sine squared of x. Well, we have a sine of x times a 0, which is always going to be 0, so that can just cancel out. So now we're left with negative cosine of x over sine squared of x. We can actually break this down a little more into two separate fractions. We can say that this is equal to negative cosine of x over sine of x times 1 over sine of x. So we can go ahead now. We know that 1 over sine of x is going to be cosecant of x. Cosine over sine is the inverse of our trig, as the inverse of tangent, I mean. And then since that's the inverse, the opposite of tangent, this is going to be equal to actually cotangent. And of course, we have that negative out in front. So therefore, our d over dx of cosecant of x is equal to negative cotangent of x times cosecant of x. And we can essentially follow this proof for pretty much for our other trig functions. So at the end of the day, for our basic trig, we can say for our trig derivative rules, at the end of the day, we can say that the derivative of sine of x equals cosine of x. The derivative of cosine of x is equal to negative sine of x. the derivative of tangent of x is equal to secant squared of x. The derivative of cosecant of x is equal to negative cotangent of x times cosecant of x. The derivative of secant of x is equal to secant of x times tangent of x. And lastly, our derivative of cotangent of x is equal to negative cosecant squared of x. So from here, we can essentially solve pretty much any rule, pretty much any function that involves any of these 6 properties. That really opens the door, so now we're not having to deal with just 2 properties. We can actually deal with 6, and also that saves us a lot. That way we don't have to just go over and convert everything that is not sine and cosine into terms of sine and cosine. So now let's go ahead and just do one quick example involving it. Let's go ahead and try to find the derivative of 1 plus tangent of x minus 1 minus secant of x. All right, so now we have our 2 functions, and now let's go ahead and apply quotient rule. Let's go ahead and apply quotient rule, which will probably be for the last time today, unless we have time at the end. But for now, let's go ahead and solve this problem. So now let's go ahead and we can let this be our f, and this is our g. So now let's go ahead, and we know that our g of x is going to be 1 minus secant of x. Our f prime is going to be, well, we have the derivative of 1 is just going to be 0, and the derivative of tan is secant squared of x. Minus our numerator, which is 1 plus tangent of x, times derivative of 1 is 0, minus our derivative of secant x is secant of x, tangent of x, all over 1 minus secant of x squared. We can go ahead and clean this up just a tiny bit. We don't have to worry about any of these zeros. So essentially we can just start distributing. We are left, and that leaves us with secant squared of x minus secant cubed of x minus secant x tangent of x minus, or plus actually, plus for both of these, since we're distributing that negative, plus secant x tangent squared of x over 1 minus secant of x squared. All right, so that's about it for our derivatives of our trig function. So now let's actually move on and cover a little bit of just some other miscellaneous properties of trig functions. So first thing I want to cover involving trig is actually going to be our limits of trig functions. So there's two main properties that we need to know when we're doing limits of trig functions. The first thing we need to know is that the limit as x approaches 0 of sine of x over x is going to always equal 1. And the next thing we need to look at is that the limit as x approaches 0 for cosine of x minus 1 over x is going to be equal to 0. These two will help you do a lot of work with limits of trig functions. I believe there's some technically other ones out there, but these are really the main ones that will be covered in this course. There's a proof of this in the textbook, however, it is kind of lengthy, and just for the purposes of time, I will not be going over it. But these are just the main two rules that you will need to understand. All right, so now let's move on and do a quick example of limits of trig functions. The first one we want to do is actually, we're going to go ahead and try to take the limit as x approaches 0 of 4x over sine of 3x. Pretend that's 3. But so this isn't quite in the form of our sine of x over x, but we can tell it's kind of similar. So we're going to actually have to go ahead and transform this function a little bit. So the first thing we can do is we want to try to at least see if we can get a 3 somewhere in that numerator. So what we can actually do is we can multiply times 3 over 3 to get 3's in both the numerator and denominator. So when we get that, we get our function ends up looking something like 3 times 4x over 3 times sine of 3x. Well, what we can actually do now is we can actually selectively pull out some of these coefficients. So what we can do is we can actually pull out this 3 and pull out this 4. So now our equation now looks something like 4 over 3. And we can actually even pull that out from the equation in front limit of, so now we are left with getting 3x over sine of 3x. Now we're actually getting kind of close here. Still not quite there, but we're getting close. Now we want to be able to actually for sure get this. Now we just need to get a 3x in the denominator down here. So actually what we can still do is let's multiply 1 over 3x and 1 over 3x to both the numerator and denominator. When we do this, this actually transforms the function into getting 1 over sine of 3x over 3x. Now we are actually in our form to where we have a sine of theta over theta. So now we have our new equation, which is the limit as x approaches 0, and we have on our numerator 1, and once again we are down to just sine of 3x over 3x. So now we have the limit is, so in our numerator, the limit as x approaches 0 of 1 is just going to be 1. In our denominator, we have x approaching 0 of sine of 3x over 3x. That is still going to just equal 1. So we can plug that in. So therefore, our final limit is going to be 4/3. Now let's try another one that's a little more challenging. This time, we want to find the limit as x approaches 0 of the cosine of 3x minus the cosine of x over x squared. All right, so this looks pretty much nothing like any of either of our identities. But there is actually something we can do to this numerator. What we're going to actually use is one of our sum identities. Now, I know they typically don't really cover these a lot in class, but there are also a lot of other trig identities out there, such as product to sum and things like that. So I would go ahead, if you have a question like this, try to look over them, and usually, don't quote me on this, but usually if they have one of these ones that you don't use super often, like the sum identities, if it's on a test, they'll give it to you. If it's on homework, they usually expect you to look it up yourself. But what we can do is there's actually a sum identity that says that if we have the cosine of sum A minus the cosine of sum B, we can actually change that to where it actually equals -2 times the sine of A plus B over 2 times the sine of A minus B over 2. What we can do now is we can actually apply this to that numerator that we have already. So what we can do is we can let 3x equal A and x equal B. So we have our limit as x approaches 0, and then we have in our numerator, we can actually transform this to where we have -2 sine of 3x plus x over 2 times the sine of 3x minus x over 2 all over x squared. We can clean up this numerator a little bit more into where we now have -2 sine of 4x over 2 times the sine of 2x over 2. Well, we can go ahead and eliminate these 2's. So now our numerator is equal to -2 sine of 2x times the sine of x. And we can go ahead and plug this back into our initial equation. Now we are actually getting somewhere. So what we can do is we can actually break this up into two separate functions, into two separate equations. So we can actually break this up into where now it's a product. So what we can actually do is we can separate this to where this now equals, we can say equals -2 sine of x over x times sine of 2x over x. Now we can take the limit of these separately and then multiply those two separate limits at the end. So first thing we can do is we have the limit as x approaches 0. We have a -2 sine of x over x, but we can actually just pull out that -2, which gets us sine of x over x. The limit as x approaches sine of x over x is just 1. So we can actually still go ahead and say that we have 2 times 1 for this particular, -2 times 1 for this limit, which is -2. Now let's look at the separate one. We have the limit as x approaches 0 of sine of 2x over x. Well, we can actually do something similar to what we did in the last one. We can actually go ahead and multiply times 2 over 2, which is going to get us 2 sine of 2x over 2x. We can go ahead and pull that 2 out from the limit to where we now have 2 times the limit as x approaches 0 of sine of 2x over 2x. The limit as x approaches 0 of sine of 2x over 2x is just going to get us 1. Now we have 2 times 1 for our limit here, which is just 2. And now we can multiply these two together and get us -2 times 2. So therefore, our final limit for this is going to be 4. So ultimately, when it comes to limits for trig functions, they're going to usually involve a lot of manipulation and usually a few of your trig identities. So moving forward, just always think about how can I manipulate this function to kind of and rearrange things to kind of get an idea of what I want and how I can get into a certain form. So now that we've covered that, the next thing I'm going to do is I'm just actually going to show you a kind of a quick little fun rule. This is just a special property for derivatives of trig functions. Or else in specific sine and cosine. So let's say if we have our f of x equals cosine of x, then we know our f prime is going to equal negative sine of x. Well, if we want to derive this again, we could say that our f prime is equal to negative cosine of x. We can keep going a little further and see that f triple prime is equal of f of x is equal to sine of x. Then we have our fourth derivative can now equal cosine of x. If we derive this one more time, our fifth derivative is going to equal to negative sine of x. So what actually happens when you have cosine, when you derive your cosine function, it actually creates a cycle the more and more you derive it. So what we can, so if you ever have a problem to where you ever have to take like a really, really high derivative of this, you can actually say that for your nth derivative of cosine of x, that is actually going to, what you can do is you can say, so if you're ever trying to find this, what you can actually do is you can divide n over 4, and then if your remainder equals 0, then that means that what you're going to get spit back out is your cosine of x. If your remainder equals 1, you're going to end up getting negative sine of x. If your remainder equals 2, you're going to keep going down and get negative cosine of x. If your remainder equals 3, we can keep going. That will get you, that will go ahead and get you sine of x. So if you this is just good if you ever have to take a really high derivative, then this kind of gives you a quick way to go ahead and do this. And if we actually pay enough attention, we see that we get a sine of x right here. And then that brings us, and we can derive that and get down to cosine, derive that again, go back to negative sine. Knowing this, knowing that sine of x is involved within that cycle, that means that, once again, it follows the same rule. It's just a little staggered from our cosine function. So if we are actually trying to find a high derivative of sine of x, once again, it has its own cycle. So you can still go ahead and divide your, the nth derivative. We have that power, divide that by 4. And then once again, we're going to end up getting this little pattern. If we do not have a remainder, then that's going to just get you sine of x. If your remainder equals 1, that is going to get you cosine of x. If your remainder equals 2, you're getting negative sine of x. And lastly, if your remainder equals 3, you are getting negative cosine of x. So once again, this is all just kind of becomes a little pattern, and then it just kind of keeps going and going and going in a circle. So yeah, it's kind of just a cool little function of this. I know there are actually instances to where you may actually have to go ahead and do this. It will likely not come up until the very, very end of this course or towards the beginning of 2414, but it's just a little good trick to keep in mind. We have a couple more minutes left, so I'm actually going to go ahead and go back to another problem I wanted to do. So let's say we want to find the derivative of 3x to the 4th plus x cubed plus 2x all over x squared. Well, there's a couple interesting things about this function. So, on the as we looked at an earlier problem, on the surface, this looks like a simple quotient rule problem. And we can go ahead and try to solve it as quotient rule, but there's actually some interesting ways we can do this. Since we have just a plain little x to the negative 2, what we can actually do is we can transform this into saying that we can actually pull this out in front and multiply it times the rest of our function. Or we can even go a step further. We can go ahead and either multiply the x to the negative 2 or divide everything in the numerator by x squared and get us a new function, to where we get 3x squared plus x plus 2 over x. Once again, we can actually go ahead and use 3 different methods to find the same derivative. So I think so let's go ahead and just try one more time, just to kind of get a better idea of how all of our rules work. So for our quotient rule, let's go ahead and start with that, since that's the form it's already in. So we know that our bottom function is going to be x squared, and the derivative of our top function, we're going to get 12x cubed plus 3x squared plus 2 minus, we're going to get 3x to the 4th plus x cubed plus 2x times 2x, all over x to the 4th. Let's go and see if we can eliminate anything on here. So we distribute, we get 12x to the 5th plus 3x to the 4th plus 2x squared minus 6x to the 5th minus 2x to the 4th minus 4x squared. All right, let's just double check. We get 5, 4, 2, 5, 4, 2. All right. So now let's go ahead, and this is all going to be over, once again, our x to the 4th. So here we can actually go ahead and you get 12 minus 6, so we get 6x to the 5th. 3 minus 2 is 1, plus x to the 4th minus 2x squared, all over x to the 4th. And we can even go a little further and say that we have 6x plus 1 minus 2 over x squared. Now let's try this again with our product rule. So we can let x to the negative 2 be our f, and we can let 3x to the 4th plus x cubed plus 2x be our g. So we have our f, x to the negative 2, times the derivative of our g, which is going to be 12x cubed plus 3x squared plus 2, plus, we're going to get a negative 2, x to the negative 3 for our derivative, and then 3x to the 4 plus x cubed plus 2x. We can go ahead and distribute everything out to where we get 12x plus 3 plus 2 over x squared, and then we get minus 6x, just minus 6x minus 2 minus 4 over x squared, which gives us 6x plus 1 minus 2 over x squared. And lastly, we can go ahead and just do our simple power rule. We have 3x squared, which is just going to get us 6x. We have to derive our x, which is just 1, and derive our 2 over x, or 2x to the negative 1. And that gets us minus 2x to the negative 2. And we can rewrite this as 6x plus 1 minus 2 over x squared. So we can see that we actually do get the same answer for all three. So whenever you're actually working on problems, especially really difficult problems, I really want you to walk away and think, okay, how many ways can I solve this and which way would be the easier? So once again, just as a recap, we went over our product and quotient rules and how they can be applied. And lastly, we also discovered our trig rules as well as our trig myths. So hopefully you all enjoyed that and have a wonderful afternoon and good luck on any future assignments.